Before you stands a wheel, 40 feet tall, built entirely from white oak beams that weigh more than most automobiles. It turns slowly, maybe 3 rotations per minute, and with each revolution, it generates enough power to run an entire factory. Looms weaving cloth, saws cutting lumber, hammers forging iron. All of it driven by nothing more than falling water and the ingenuity of men who never saw a light bulb in their lives. This is not ancient history. Your great-great-grandfather might have worked in a mill powered by one of these wheels. He might have spent 12 hours a day listening to the thunder of water against wooden buckets, feeling the floor vibrate beneath his feet, watching the massive axle turn with a force that could crush a man without slowing down. We talk about the Industrial Revolution like it was powered by steam and coal, and eventually it was. But before the steam engine became reliable, before coal became king, there was water, rivers and streams and mill ponds that turned wheels, that turned gears, that turned the machinery of a growing nation. For nearly 200 years, water was America's primary source of industrial power, and the men who harnessed it built some of the most remarkable machines this country has ever seen. You will never find their names in history books. The millwrights who calculated the exact pitch of wooden buckets to capture maximum force from falling water. The carpenters who shaped white oak timbers into wheels that would run for a century without replacement. The laborers who dug the channels and built the dams and maintained the machinery that kept entire communities alive. These men understood physics they could not name. They built engines from trees, and most of them are completely forgotten. This is the story of how America built 100-ton water wheels that powered entire towns. How wooden machines worked for 100 years without breaking. How an entire civilization ran on nothing but rivers and craftsmanship. And what we lost when we decided electricity was more convenient than understanding the world beneath our feet. To understand why water wheels mattered, you need to understand what America looked like before them. Picture the colonies in 1700. Most people are farmers. They grow their own food, raise their own animals, make their own clothes. Everything requires labor, and labor requires time. And time is the one thing nobody has enough of. Grinding grain into flour takes hours by hand. A woman with a hand quern, basically 2 stones that rotate against each other, might process enough wheat for a single loaf of bread in 30 minutes of exhausting work. Sawing lumber for a house means 2 men operating a pit saw, one standing above the log and one standing in a pit below, she pulling a blade back and forth for hours to cut a single board. Fulling cloth, the process of cleaning and thickening woven fabric, requires workers to stomp on wet wool for days at a time. This is the world before mechanization, a world where every product requires human muscle, human hours, human exhaustion. And the limiting factor on everything, how much food you can grow, how many houses you can build, how much cloth you can produce, is how many people you have and how hard you can work them. Now picture a river. It flows whether you watch it or not. It flows while you sleep. It flows on Sunday, and it flows in winter, and it flows regardless of how tired you are. It never stops, never complains, never demands wages. And it contains more power than 1,000 men working together. The physics are simple. Water has weight. When it falls, that weight becomes force. If you put something in its path, that force becomes motion. A wheel placed in a stream will turn, and a turning wheel can drive machinery. The Romans knew this. The medieval Europeans knew this. The colonists who came to America knew this. But knowing it and doing it are different things entirely. The first water wheels in America were small, maybe 6 feet in diameter, simple undershot wheels where the water flowed beneath the wheel and pushed against flat paddles. These could grind grain for a family, maybe a small village, but they were inefficient, and most of the water's energy was wasted as splash and turbulence. Then came the overshot wheel. Instead of pushing against the bottom of the wheel, water was channeled to the top and poured into buckets. Gravity pulled those full buckets down, turning the wheel. When the buckets reached the bottom, they emptied, and the cycle repeated. This design captured far more energy. A well-built overshot wheel might convert 60 or 70% of the water's potential power into usable rotation. But building an overshot wheel meant building infrastructure. You needed a dam to create a mill pond, a reservoir that stored water and maintained consistent flow. You needed a head race, a channel that carried water from the pond to the top of the wheel. You needed a tail race to carry the spent water away. You needed the wheel itself, massive and precisely balanced, and you needed gearing to convert the slow rotation of the wheel into the faster rotation required by machinery. This was not a weekend project. Building a working mill was one of the largest construction efforts a colonial community would undertake. It required specialized knowledge, significant capital, and months or years of labor. The men who possessed this knowledge, the millwrights, were among the most valued craftsmen in America. A millwright was part engineer, part carpenter, part blacksmith, and part magician. He had to survey the landscape, calculate water flow rates, shall determine the optimal wheel size, design the gearing system, supervise construction, and then troubleshoot problems when things inevitably went wrong. There were no engineering textbooks, no standardized training programs. Knowledge passed from master to apprentice through years of hands-on work. A good millwright could look at a stream and tell you within a few percentage points how much power it could generate. He could calculate gear ratios in his head. He could feel when a bearing was wearing out by the vibration in the floor. These men built America's first industrial infrastructure, and they did it with hand tools, local timber, and an understanding of water that bordered on the intuitive. The wheels grew larger as ambition grew larger. By the late 1700s, mills were being built on major rivers with wheels 20, 30, even 40 feet in diameter. These were not improvements on earlier designs. They were entirely different categories of machine. Consider what it takes to build a 40-foot water wheel. The main shaft, the axle that the wheel rotates around, might be a single white oak timber 3 feet in diameter and 40 feet long. Finding such a tree required searching deep into old-growth forests. Felling it required days of work with axes and crosscut saws. Transporting it to the mill site required teams of oxen and specially built sleds. Shaping it into a perfectly round axle required skilled workers with draw knives and planes working for weeks. The wheel itself was assembled from hundreds of individual pieces, spokes radiating from the central shaft, rim sections curved and joined with mortise and tenon joints, buckets or float boards attached at precise angles. Each piece had to be shaped by hand. Each joint had to be tight enough to withstand decades of constant stress. The finished wheel might weigh 50 tons or more, and it had to be balanced. A wheel that heavy, rotating constantly, would tear itself apart if one side were heavier than the other. Millwrights used lead weights embedded in the rim to achieve perfect balance. They could detect imbalances of a few pounds in a structure weighing thousands. They did this by feel, by watching the wheel turn, by placing their hands on the timbers and sensing the vibration. Once the wheel was built, it had to be installed. This meant lifting those 50 tons into position on the shaft, aligning everything perfectly, and connecting the wheel to the gearing system. There were no cranes, no hydraulic jacks, no power tools. Men accomplished this with rope and block and tackle, with wooden scaffolding, with coordinated effort and accumulated knowledge. When the water was finally released and the wheel began to turn, it must have seemed like witnessing the creation of a new kind of life. This massive structure, built entirely by human hands, suddenly moving with a power no human could match, the floor trembling, the gears engaging, the machinery coming alive. The mill was ready to work. The most famous water wheels in America were built at Lowell, Massachusetts. In the 1820s, a group of Boston investors decided to create an entirely new city dedicated to textile manufacturing. They chose a site on the Merrimack River where a 30-foot waterfall could be harnessed for power. And then they built something that had never existed in America before, an integrated industrial complex where water powered everything. The Lowell system used a network of canals to distribute water to multiple mills. Each mill had its own wheels, some of them among the largest ever built. The water flowed from canal to wheel to tail race in a continuous cycle, generating power 24 hours a day. At its peak, when Lowell's system generated more horsepower than any other industrial site in the Americas. But Lowell was not unique. Similar complexes were built on rivers throughout New England and the mid-Atlantic states. The Brandywine River in Delaware powered a network of mills that produced flour, paper, and gunpowder. The Blackstone River in Rhode Island became one of the most industrialized waterways in the world, with mills every few hundred yards along its length. The Patapsco River in Maryland, the Housatonic in Connecticut, the Susquehanna in Pennsylvania. Anywhere water fell, wheels turned. These were not quaint rural operations. They were industrial facilities that employed hundreds or thousands of workers. They ran 3 shifts, 24 hours a day, 7 days a week. The wheels never stopped turning. The machinery never stopped running. The workers, many of them young women recruited from New England farms, never stopped working. The sound of a working mill is something you would remember for the rest of your life. Start with the water itself, roaring through the head race, crashing against the buckets or blades of the wheel. Add the groan of the main shaft turning in its bearings, wood against wood or wood against iron. Layer on the clatter of gears meshing, the rhythmic thump of trip hammers, the steady drone of looms or grindstones. Mix in the human sounds, shouted conversations barely audible over the machinery, footsteps on wooden floors, the occasional scream when something went wrong. You would feel it as much as hear it. The floor vibrated constantly. The walls vibrated. Your teeth vibrated. After years of work in a mill, that vibration became part of you. Old mill workers reported feeling phantom vibrations in their bones decades after they had stopped working. The smell varied depending on what the mill produced. Grain mills smelled of flour dust and oil. Textile mills smelled of wet wool and machine grease. Sawmills smelled of fresh-cut pine and sawdust. All of them smelled of water and that particular mineral scent of flowing rivers. Working conditions were brutal by modern standards. 12-hour shifts were common. 14-hour shifts were not unusual. The machinery was dangerous and unguarded. Gears that could catch a sleeve and pull an arm into the mechanism. Belts that could grab loose hair and scalp a worker in an instant. Shafts that spun with enough force to kill anyone who fell against them. There are no complete records of how many workers died in American mills. Death was common enough that it barely warranted mention in most accounts. A hand crushed in the gears. A body pulled into the machinery. A worker who fell into the mill race and drowned. These tragedies happened regularly, and the mills kept running. The wheels did not stop for death. The wheel could not stop. Stopping meant lost production. Lost production meant lost profit. Profit was what the mills existed to create. The workers who survived accumulated injuries, hearing loss from years of constant noise, respiratory problems from breathing flour dust or cotton fibers, joint damage from repetitive motions, burns from steam or friction. These injuries were simply part of the job. There was no workers' compensation, no disability insurance, no retirement plan. When you could no longer work, you stopped earning. And what happened after that was your problem. And yet, people kept coming. The mills offered wages, and wages offered independence. A young woman who worked in a textile mill for a few years could save enough money to marry with a dowry. A young man could learn a trade and eventually become a skilled worker, earning decent wages. The mills were harsh, but they were also opportunity. They were also the future. The men who built and maintained the wheels occupied a special position in the mill hierarchy. Millwrights were skilled craftsmen who commanded respect and relatively high wages. They understood the machinery in ways that operators did not. They could diagnose problems from subtle changes in sound or vibration. They could perform repairs that kept the mill running and the workers employed. A millwright's tools were simple but specialized. Chisels and planes for shaping wood. Files and hammers for working metal. Measuring instruments, calipers and levels and plumb bobs for ensuring precision, and always a notebook where they recorded calculations and observations that would inform their next project. The knowledge they possessed was not written down in any comprehensive form. Each millwright learned from a master, absorbed years of accumulated wisdom, and added his own observations before passing everything to the next generation. This oral tradition meant that knowledge was both preserved and lost with each generation. When a master millwright died without fully training a successor, decades of specialized understanding could disappear in an instant. The wheels themselves required constant maintenance. Wood absorbs water and swells. It dries out and shrinks. It rots. Even the best-built wheel needed regular attention. Buckets had to be replaced. Bearings had to be lubricated. Joints had to be tightened. A neglected wheel would fail, and a failing wheel could destroy a mill. The most skilled millwrights developed an almost mystical relationship with their wheels. They could tell when something was wrong before any visible sign appeared. They spoke of the wheel feeling different, of sensing imbalances or wear through their hands and feet. This intuitive understanding was real. Years of experience had trained their nervous systems to detect patterns too subtle for conscious analysis. Some wheels ran for decades without major repair. Others required constant attention. The difference usually came down to the original construction. A wheel built with properly seasoned timber, carefully balanced, installed with precise alignment, might run for 50 years with only minor maintenance. A wheel built in haste, with green wood or sloppy joinery, might fail within months. The great irony of water power is that it was always limited. A river can only generate so much power. Once you have harnessed all the available fall at a site, you cannot get more. You can improve efficiency, capture a higher percentage of the water's energy, but there is an absolute ceiling determined by the volume of flow and the height of the fall. Steam power had no such limits. You could build a steam engine anywhere, regardless of geography. You could make it as powerful as you wanted by making it larger. You could shut it down when you did not need it and start it up when demand returned. Steam was flexible in ways water could never be. By the mid-1800s, steam engines were beginning to replace water wheels at industrial sites across America. The replacement was gradual. Water power was cheap once the infrastructure was built, while steam required constant fuel. Many mills ran hybrid systems, using water when it was available and steam when it was not. But the trend was clear. The future belonged to fire, not water. Then came electricity, and electricity changed everything. A waterfall in a remote location could now generate power that was transmitted hundreds of miles to cities and factories. The wheel itself became unnecessary. Water turned turbines that generated current that flowed through wires to wherever it was needed. The physical connection between power source and power user was broken. Within a few decades, the great water wheels fell silent. Mills were abandoned or converted to other power sources. The canals that had distributed water to dozens of factories became drainage ditches or were filled in entirely. The millwrights who had understood this technology aged and died, and their knowledge died with them. Today, a handful of working water wheels survive. Some are tourist attractions, restored to demonstrate how our ancestors lived and worked. Others continue to operate at small scale, grinding grain or generating modest amounts of electricity. But the era of the great industrial water wheel is over. It lasted barely 2 centuries, and then it was gone. What remains is harder to see, but perhaps more important. The mills powered by water wheels created the first American manufacturing sector. They produced the cloth that clothed a growing nation, the flour that fed it, the lumber that housed it, the iron tools that built it. They created jobs that drew workers from farms to factories, beginning the urbanization that would transform American society. They generated capital that funded railroads and banks and new industries. They proved that manufacturing could work in America, that we did not need to depend on European imports. The workers who labored in these mills, the millwrights who built and maintained them, the investors who funded them, the communities that grew around them, all of them were part of a transformation that made the modern world possible. They did not know they were making history. They were just making a living, but their labor accumulated into something larger than any of them could have imagined. There is a philosophical dimension to water power that steam and electricity lack. A water wheel is comprehensible. You can see how it works. Water falls, the wheel turns, gears mesh, machinery operates. Every step is visible and mechanical. There is no mysterious conversion, no invisible energy. Just mass and motion and the ancient physics of falling water. Steam engines obscured this clarity. You burned fuel, created pressure, and somehow motion resulted. The connection between cause and effect was real but invisible. You could not watch the steam molecules doing their work. Electricity removed causation from the picture entirely. Flip a switch and something happens. Why? How? The answer requires understanding physics that even most educated people cannot explain. We have traded comprehension for convenience. We use power we do not understand, generated at facilities we never visit, transmitted by processes we cannot visualize. The millwrights who built America's Waterwheels possessed a deep understanding of the forces they harnessed. They could explain exactly how their machines worked because they had built every component with their own hands. They understood the relationship between input and output, between cause and effect, and between intention and result. This understanding gave them a kind of mastery that is increasingly rare in our specialized, abstracted, electrified world. Perhaps this is romantic nostalgia. The past was hard and brutal and short, and water power was part of that hardness and brutality. Workers died in mills. Children labored alongside adults. Rivers were dammed and diverted and polluted. Progress always has costs, but there is still something worth remembering in how those wheels worked. The elegance of harnessing gravity, the skill of shaping wood into precision machinery, the patience of building something meant to last a century, the community that formed around a shared power source. These things had value, and some of that value was lost when we moved on to newer technologies. The rivers still flow, the old mill sites are still there if you know where to look. A few stone foundations, some rusted iron, maybe a dry canal bed or an abandoned mill pond slowly returning to forest. These are the archaeological remains of America's first industrial age. They deserve better than forgetting. So the next time you flip a light switch, take a moment. Think about the river that might be generating that electricity. Water falling through turbines in a process descended directly from those first simple water wheels. Think about the workers who stood in roaring mills and fed the machines that built our world. Think about the millwrights who understood physics they could not name and built engines from trees. They powered a revolution with nothing but falling water and wooden wheels, and we are still riding the momentum they created,